All right, thanks a lot. Thanks, Andy, and welcome everyone to Spark Summit Europe. We're really excited to have you here. So we have a really exciting and packed program for you in the next 2 days. This is our largest European Spark Summit, and we have 102 different talks, 1,200 attendees, and 11 different tracks of content. And you probably physically won't be able to attend all the talks. All the material will be available online after too, so we hope you really enjoy it. So in my talk today, I wanted to give you an update on 2 of the areas that we at Databricks and also the community have been working heavily on this year in Spark, namely streaming and deep learning. But before I do that, I also want to talk a little bit about the other things going on in the project, because there's a lot of other stuff that I'm not going to be able to cover in detail. So this year, there's been quite a bit of development in Apache Spark. Some of the biggest items added include cost-based optimization in Spark 2.2, lots of Python and R improvements, including publishing Spark to the standard package repositories here, so you can easily import it in applications, and a lot of performance work. And also, there's quite a bit of work happening in the community on support for Kubernetes, which is also targeting Spark 2.3. Just one thing I wanted to highlight out of these items is actually the Python performance work. A feature recently added in the master branch is vectorized user-defined functions, which allow you to pass batches of data in Python using Apache Arrow and process them using pandas. And that makes it much faster to write Python applications. And one of the kind of results of that is that actually Spark is becoming a really solid way to parallelize Python even when you're working on a single machine. So the graph on the right there is showing if you just do single machine data processing, you actually can get a lot of speed up using Spark. So this is one of the things I'm excited to see, and that will continue developing. Apart from the code itself, one other announcement I wanted to make is about books. So Bill Chambers from Databricks and I have been working together on this book that Bill is leading, which is Spark the Definitive Guide. It covers all of the new APIs in Spark 2.0 and structured Spark in particular. And I'm happy to also announce that Databricks is making some preview chapters from this book available for free, including the code if you want to run the exercises. So the book will be out later this year. We actually have some physical early editions at our at our booth, but you can also check it out online. So now let's get to the main topics I wanted to talk about, which are streaming and deep learning. So these are 2 of the fastest growing workloads for big data applications in general, whatever scale you're at. And they're 2 of the things that we've been working on heavily in Spark in the past year, together with others in the community. And basically, both streaming and deep learning are important workloads, but they're very complex to implement using current tools. I think no one will argue that these things are simple. And we think that we can actually simplify both of them a lot with Apache Spark, and I'm going to talk about how we're doing that. So to start with, let's think about why are streaming and deep learning hard. And the point I want to make here is that they don't need to be intrinsically hard, but just the tools are at a stage of evolution that's early on. And it's actually very similar to the situation in early big data tools, such as MapReduce. Basically, if you look at the evolutions of these systems, you had these early systems that showed there's tremendous potential in kind of a new way of computing. For example, with MapReduce, for the first time, you could easily write applications that run on thousands of servers and tens of thousands of disks. But just the first tool, that's the first one to do this, isn't enough to make it easy to write complete end-to-end applications. So these early tools were quite difficult to use at first as part of a larger workflow. And this kind of for 2 reasons. First of all, they had low-level APIs, such as MapReduce, where you still have to do a lot of the plumbing yourself. And second, there were just different systems, isolated systems for each task you want to do in your workflow. For example, if you remember the early MapReduce and cluster computing tools, there were separate tools for SQL, graph processing, ETL, machine learning, and so on. And of course, any real application combines lots of these, and you just get the joy of managing one distributed system, now multiplied by 3 or 4 times to write a complete application. So it's not easy. So Spark was one of the systems that tried to make this a lot easier, and I think did a good job of this for big data. And in Spark, there were two key ideas that made it possible. The first was to have composable, high-level APIs that let you build your application out of standard components and just hook them up and get something that works. So in Spark, these are all the built-in libraries like MLlib and Spark SQL and so on. You can hook them up in any order you want and get a program that still works and is efficient. And then the second part is a unified execution engine that can actually execute complete end-to-end applications. So you no longer need to run 3 or 4 different systems just to hook together, kind of a simple data pipeline. You can actually run them in one, and not only is it simpler to operate, but it will actually optimize the whole thing end-to-end. So these are the ways that it made it possible to build these end-to-end applications. And we think the same things apply in streaming and deep learning, and we've been working to try to make this possible through extensions to Apache Spark. So I'm going to start by talking about streaming, especially structured streaming, which is the high-level API that we've been building over the past year. So streaming today is fairly complex, mostly because it requires different APIs from other processing systems you have, and also different systems that you have to operate. And most streaming systems today, they are very powerful. You can write sophisticated applications, but you need to think in a streaming fashion and learn about all these operators and concepts that apply only to streaming. In structured streaming, we wanted to take a very different approach, which is to design a high-level end-to-end API that lets you write complete applications. And the first element of that approach is having a much simpler interface. So instead of telling you to learn something streaming specific, the interface here is just give us a program, say, using data frames or using Spark SQL that computes what you want. And if you wrote that program and it computes the result you want, we're just going to execute it in an incremental fashion. So we figure out how to update that result as new data arrives. So the outcome here is that if you know how to write a batch computation that computes something, it's very easy to run the same thing in a streaming fashion. You don't change your code at all, and now you get results efficiently in an incremental fashion. So it makes it much easier to write these applications. The second component is that structured streaming is designed for complete end-to-end applications. So, for example, a lot of people we talk to say, well, streaming by itself is good if I want to run a map function on a stream of data, but what if I want to join this with some other data source? What if I want to periodically make sure it syncs up with a batch job? Or what if I want to query the data interactively? So these are all things you can do with Spark, and in structured streaming, you can do them in the same application and also in the same code base as you're streaming. So while the job is running, you can join with static data, you can run batch jobs and so on much more easily than having different systems. And then the final thing is we wanted to make it less complex to manage. So all of the APIs and implementations are built for end-to-end reliability and transactional exactly once processing. So you don't have to think about, well, what type of sink is this? What type of source? Where am I storing the state? And so on to make it reliable. Just any way you combine these, it will actually be reliable. Structured streaming started as a project last year, and it's gone a long way since then. So in the Spark 2.2 release this summer, it was marked as generally available, which means the API is stable now, and the community thinks it's ready for production. And since that time, we've actually seen very rapid growth in the usage of structured streaming. So just as an example, at Databricks, we operate a cloud service with over 700 customers running big data applications, and we already measure hundreds of customer applications that are in production, by which I mean they're running 24/7. They're not just someone doing development and experimentation. This is across our cloud platform. The largest of these applications process tens of trillions of records per month and petabytes of data per month. So this scales to the same extent as anything else in Spark would, and is able to handle these applications. Just as some example of use cases that we've seen, a lot of these actually appeared at Spark Summits in the past. Viacom uses structured streaming to monitor the quality of live video across all its websites. So if you think about it, live video delivery, imagine you're watching something like a broadcast or a sports game or something like that, is something where it's very important to make sure the data is delivered reliably. If you have any problem delivering it to, say, customers in one internet provider, they're going to miss out on that live stream for minutes, and that means they'll miss the most important parts of the content. So it's important to monitor and fix the issues with it in real time. And Viacom built their system using structured streaming to do this across all the ways that it can deliver video and make sure it provides high quality. Second example is iPass. iPass is actually the world's largest operator of Wi-Fi hotspots. If you connect it to a hotspot at your hotel or in a coffee shop or possibly even the one in the venue here, it's very likely that one of those is running iPass. And iPass is using structured streaming for anomaly detection across all these hotspots, because you can imagine it's very difficult to manage this many hotspots and make sure they all achieve high performance. And then finally, Riot Games is actually it operates the world's largest online game, League of Legends, and it's using structured streaming to do real-time analytics in that. So what does structured streaming actually means in terms of coding up applications? As a simple example, I'm going to show the Yahoo streaming benchmark, which is just kind of a simple application people have used that basically counts ad campaigns and joins a stream with historical data. So first, let's look at the API. I put a more kind of traditional streaming API on the left, which is Kafka Streams. Other systems look at it like this too. And I put Spark data frames on the right. So you can see, first of all, there's a lot less boilerplate. You don't have to define types everywhere and parse things in the middle of your application and so on. So that's kind of nice. But the second thing that's interesting about the data frame code is it's actually the exact same code you just run on a static piece of data. If you just had a table of events and a table of campaigns and you wanted to filter them and join them, you would run this code. So you don't need to change your code to run in a streaming fashion. And what's happening under the hood is that Spark sees the batch execution plan for this computation, and it can automatically transform it into an efficient streaming execution plan, including maintaining state and doing transactional updates. So you don't have to think about how to do those pieces yourself. Now, how does this affect performance? Usually when you have high-level APIs, it means you lose out in performance. But it turns out that for structured streaming, the API actually helps with both. So we looked at the performance of the Yahoo benchmark on several different systems, and we looked also at numbers published by others. We ran this on 10 servers. So first of all, if you just run Kafka Streams, it achieves around 700,000 records per second for this benchmark. Sounds like a lot, it's hundreds of thousands of records per second, but we are running 10 servers here, and they actually have a lot more computing power than that. So it's not necessarily the most efficient way of running this application. If you look at Apache Flink, data artisans published a blog post where they optimized Flink for this benchmark, and they were able to achieve 15 million records per second on the same hardware, and it's actually much closer to kind of the hardware limits here. And finally, when we run structured streaming, same application, same hardware, we were able to get 65 million records per second using the code I showed before. So how does this happen? Why does this happen? Well, structured streaming reuses all the optimizations that are in Spark SQL, namely the Spark SQL query optimizer and the Tungsten execution engine. And many years of effort have gone into these to make big data processing extremely fast using these tools. So it actually inherits the efficiency of Spark SQL, and that makes a major difference over these streaming-only engines. What does this actually mean for you? Well, it's about 4 times faster on the same hardware. One thing it means is 4 times lower cost. If you're operating this 24/7, you might care about that. Why should you keep all these machines up all the time to do the stream processing? But the second, more subtle thing it means is you're also operating 4 times fewer nodes. So if you think about it, significantly less maintenance burden. It means failures will happen 4 times less often, and so on. So your application is actually much easier to manage as well. Finally, I talked about throughput here, but what about latency? What if you want ultra-low latency? This is something that Spark didn't optimize for as much in the past, but that structured streaming provides a path to do better. So in development, there's this continuous processing mode that can run structured streaming applications without micro-batching. Prototypes show that it's able to achieve less than a millisecond of latency, same as latency-optimized systems, and there are no changes to the user code. It's the same API. So this is still kind of in early development now, but there's a proposal and design up on the Jira website, and you can follow this. The target is to have a first version of this in Spark 2.3. The key idea that makes all of these features of structured streaming possible is that the same API, this declarative SQL-based API, can be compiled to both streaming and batch. And this is what we think will make it much easier to write streaming applications. And if you want to find out more about structured streaming, we have a deep dive this afternoon, 1-hour deep dive, where you can learn about how to use it and how it works. So that's kind of the streaming side. We think we can really simplify streaming in most of the common use cases using this kind of API. And next, I want to talk about deep learning. Deep learning, like streaming, is one of these technologies that has huge potential. It gives us an unprecedented ability to work with unstructured data, such as images and text, mostly because deep learning can learn how to featureize data in addition to learning models on top of it at the same time. And of course, it's achieved amazing results in many different areas of machine learning in the past few years. But deep learning is also difficult to use. The current APIs, like TensorFlow and Keras, are fairly low level when you think of the end-to-end task a user is trying to achieve. In particular, these APIs focus on building a computation graph from scratch, and they're really designed for people who want to author new models and change this layer here, change that layer there. But that's often not the main thing you do in a production application. Scale-out under these APIs usually requires manual parallelization. You have to add your own code in TensorFlow to decide what to run on each machine and so on. And finally, once you've built your models, it's actually pretty painful to use them in large applications. For example, you can run a serving system like TensorFlow Serving, but now you have to manage some other distributed system that's running. So the state of this, I'm going to argue, is actually pretty similar to the early big data tools, where you had the first tool that could really do something, but it wasn't integrated into the end-to-end workflow. Given this, there's been a lot of work on supporting deep learning in Spark, and in particular integrating with the rest of the unified engine and environment that Spark provides, so you can actually do the end-to-end application in one system. So some examples are adding images as a first-class type in MLlib, which is happening in Spark 2.3. Lots of integrations with deep learning frameworks, including TensorFlow, CNTK, and others. And finally, kind of my favorite thing is trying to figure out higher-level APIs that make the common use cases much simpler. And at Databricks, we launched this API called Deep Learning Pipelines. Just to talk about the framework integrations, these are for advanced users who want to code stuff in TensorFlow. One of the things that we've been collaborating on at Databricks is TensorFlowOnSpark. So this is a widely used library that originated at Yahoo that launches distributed TensorFlow jobs inside a Spark cluster and can feed them data from RDDs and data frames. So you can just mix TensorFlow and Spark processing in the same workload. And it powers dozens of applications at Yahoo, including photos, videos, and content recommendation. This summer, we've been working with Yahoo to add 2 features that make this much easier to use. ML pipeline APIs, so you can integrate this into ML pipelines, and then support for non-yarn clusters, so you can actually run this in other Spark environments. Both of these are in TensorFlowOnSpark now, and I encourage you to check it out, or actually to see the talk about it tomorrow afternoon that will go into detail about how it works. And then the second library I want to quickly talk about as a different kind of angle on the problem is deep learning pipelines. So these low-level deep learning frameworks like TensorFlow are powerful for writing new models, but they don't make it that easy to write common use cases. And we want common use cases to be much easier to build. So the goal of this library that we started is to enable an order of magnitude more users to build production applications using deep learning. Notice there are 2 parts. There's more users, so make it much easier to use, but there's also the production part. We want to make sure this is not just something you can do as an example once, but something you can actually use reliably thereafter. And the approach that we're taking here is to design the API based on ML pipelines. ML pipelines are a standard way, probably the best way we know of modularizing machine learning applications. They're used in scikit-learn, and of course, they're used in Spark. So what this gives us is that common use cases are just a few lines of code in the pipeline API. All of the operators in this library are designed to scale out automatically, so you don't have to worry about how to scale out your code. And finally, it's also very easy to take the models you built and expose them in other parts of Spark, including SQL queries, streaming applications, and batch jobs. And all of this builds on existing deep learning engines like TensorFlow and Keras. So just as a few quick examples, first I'm going to show using just applying an existing model, which is a common thing you might do. You can load common models just by name and then apply them to data frames using the ML API to transform them. And if you want, you can also export either the standard models or the ones you built in SQL. So now anyone using SQL in your organization or any kind of business intelligence tool can actually also call into these models very easily. It's a really powerful way to use this. As a second example of what you can do, this is a feature we recently added to the library. It's parallel model search. So everyone who does deep learning knows you have to tune lots of different parameters to get a good model. And using Spark, using the grid concept in ML pipelines, you can just set up a grid of parameters and run all the experiments in parallel on a Spark cluster and get a nice fault-tolerant way of executing all of them and finding the same model. So I can, and this is something that would have taken lots of code and lots of manual parallelization to build in something like TensorFlow. So I can keep talking about why this is simpler, how much less code, and so on, but I think it's much more exciting to see it in action, to actually build something using it. And for this purpose, I'd like to invite Suan Hong, who's a software engineer on the ML team at Databricks, to give you a demo of deep learning pipelines.
Thanks, Matei. So I have a confession to make. I like shoes a lot. Some people, like my husband, might say I have a shoe problem. But today I'd like to show you that this is really a data problem. This is what shoe shopping looks like. So here's Zappos.com, one of my most frequently visited websites. And one of the first things to notice here is that in women's shoes, there are 34,677 pairs of shoes. That's a lot, which is really exciting for me, but it's also daunting. So how should I go about finding a pair of shoes I like on this website? Fortunately, there are some ways to narrow down my choices. Unfortunately, it looks like this. There are 16 different ways to characterize your shoes, each with tens of values, and these are not mutually exclusive. So unlike configuring, let's say, a data center server with exact specs, searching for shoes is really an inherently visual task, which calls for a more visual experience. And it's possible to provide one. So for example, this website, given a pair of shoes you're interested in currently, recommends a bunch of shoes that are visually similar. And underneath this is some pretty powerful machine learning, very likely powered by deep learning used for image analysis. So the question is, why isn't this sort of more intelligent experience the norm? Or why isn't deep learning everywhere? So as Matei pointed out earlier in his talk, there's a common set of challenges when it comes to applying deep learning to problems. One is that to train a single model can take a lot of compute resources and time. Often on specialized hardware, it can take days, if not weeks. And even if you have those resources, it takes a lot of manually intensive parameter tweaking to create a great model for your task. So these two things combined means it can take months to get a good model for the task at hand. And because deep learning models are complex, it means it requires a lot of often labeled data to train a great model. So deep learning pipeline solves these problems by using the Apache Spark for its elastic scale-out power, using MLlib pipelines API to concisely capture the deep learning workflow for common workflows, and As one of its core features, it offers transfer learning from pre-trained models out of the box, which requires a lot less labeled data or even no labeled data than training your own model from scratch. So today we're going to build a visual recommendation AI like the one we saw earlier, but we're going to do it in 10 minutes with 7 lines of Spark code and 0 labels. So let's go to the demo, please. OK. So here, in this Databricks notebook, we've loaded a data set of women's shoes images. And there are about 34,000 of them, not unlike Zappos. Let's look at what the images look like. OK. So there's a pretty good variety of shoes here, from high-heeled pumps to athletic running shoes, tall boots, summer sandals, ankle boots, and so on. So now, as a data scientist, given a particular pair of shoes, how should I go about finding similar items? One natural algorithm to consider is nearest neighbor. For those who might not be familiar with it, nearest neighbor works by assuming that your data points in the data set lie in a space, a vector space, such that things that are more similar are closer together than things that are not as similar. So this means to find the top k most similar items, you can find top k nearest items in the space. And one interesting fact about nearest neighbor is that it actually requires no labels. It just requires that your data be represented in a reasonable way. So one first thing you can try here then would be to take the raw images, the image pictures themselves, and try this nearest neighbor algorithm. Right? So here we've also loaded the images as one-dimensional vectors. It just looks like a vector. There's a lot of white background. But another interesting thing about it is, if you look at the shape, each image consists of 500,000 numbers, so it's in a very high dimensional space. So if you've worked with nearest neighbor type of algorithms before, you might be like, is that going to work out OK? We'll see how it works. But also importantly, this means computing the distance between the items can be a non-trivial task. And that's bad because to find the top k most similar items, you need to compute the distance between that given item and everything else in the data set, which can be very expensive. But because we're using MLlib, we're in luck. It provides a very fast approximate nearest neighbor algorithm called locality-sensitive hashing, or LSH. And briefly, this algorithm works by, for each item, finding an approximate neighborhood really quickly using hashing, as you might guess. So that to find the top k nearest neighbors, you only need to search in this approximate neighborhood instead of the entire data set. So let me run this real quick. OK. Here we've written a little helper function called runLSH. We're going to use an LSH algorithm called bucketed random projection LSH, which essentially just computes the Euclidean distance between the items. After creating the object, we can call approx nearest neighbors with the candidates, which will be all the shoes, key, which is the original shoe. And here we'll find 10 nearest neighbors, or top 10 most similar items. So these are the 4 lines out of the 7 that I promised. So let's look at what happens when we run this on the raw image, the original image. This is the shoe. This is the pair of shoes of interest. And here are the similar items I found. I say they're not horrible. They kind of have the same shape-ish, definitely in the same color space, black and beige. But I started out looking for these sort of airy summer sandals and ended up with furry slippers, which look really comfortable, but not really what I was looking for. So as a data scientist, I look at this and say, this is not quite production ready. All right, so what do? obviously, we're going to use deep learning. Could we go to the slides back? OK, cool. To talk about how we're going to use deep learning here today, it's useful to start with the more traditional supervised learning scenario, where we have a deep learning model here, which is a neural network, that takes an image and it outputs a label or a set of labels that describe what's in it. So this particular task is called image classification. And it's a well-known problem, but not a trivial one. Luckily, there's been decades of research that went into this by hundreds of researchers, such that now we have a series of really great models that can do this. And these models have been trained on millions of images, usually on this one data set that has 1,000 categories, including things like pandas and cars and daisies and so on. But the key insight here is that these models have become so sophisticated that the intermediate layers are able to capture higher level concepts about the image, such as these edges, blobs, textures, and even whole objects inside. So what this means is that we can take such a network trained on these millions of images that actually don't really include any shoe-specific information, but we can chop off the top layer that gives you the label, take an intermediate representation, and we'll get what's called an embedding, where now this network takes an image and projects it into a lower dimensional space, such that things that are more similar should be closer together, and things that are not supposed to be similar should end up further away. So now with this applying deep learning, we believe that we have a more semantically meaningful space to work with, which is great news for nearest neighbor. So let's see how we can do this in code. All right, great. Deep learning pipelines provides a tool called Deep Image Featurizer, which actually does exactly this. So you can make a Deep Image Featurizer object specifying just the model name. Here we'll use Inception v3. It supports other popular models as well. And when we call transform using this featurizer on the image data, it will output exactly that embedding we just talked about that should be in a more meaningful space. So we're going to run the exact same LSH nearest neighbor algorithm just in that new space. And again, here's the original shoe. And the results are much better. And not only is this now able to find shoes that are basically the same shape with different colors, it's able to capture things like the texture, such that it can find shoes that are different styles, but have the same detailing, like this crochet detail here. And could you go back to the slides, please? OK. And just for fun, these are the similar images for the sample set we had before, which I would say are really pretty good. For those non-shoe aficionados, it may not be obvious, but for example, not all tall boots are created equal. They have different boot heights and different detailing. And here, we actually have very similar height boots with this buckle detail around the ankle, which is pretty great that this network can capture that. And we were able to build this in just 10 minutes using the power of Apache Spark for scaling out. We didn't run it here today, actually, but the step to take the images and transform them into the embedding space takes only 10 minutes on Spark. That's why it takes 10 minutes to build this. But it takes 6 hours on a single node Keras workflow, which is the difference between almost an entire day's worth of work versus a coffee break. And we were able to do this in 7 lines of code thanks to the simplicity of MLA pipelines. And we did it with 0 labels by leveraging the power of deep embeddings, which was able to capture these higher level concepts about images, even though this particular model was not at all trained on shoe-specific data. And these elements capture the sort of philosophy behind deep learning pipelines, which aims to make production AIs for common tasks as easy to build as what we saw today. So check out deep learning pipelines. We have a deep dive session at 2 p.m. today. There's a bunch of other tools it offers if you want to create your own model for a very different task, for example. And imagine what deep learning can do for you, and try it out. Thank you.